Greetings and welcome back. Today we'll be looking at how to draw reaction mechanisms, and in doing so we're going to be considering the four major types of reaction mechanisms. I want you to see all of these as being very similar, and so we're going to really get into the electron's point of view as to how and why these reactions happen. I would say that arguably this is the single most important lecture of the entire year of organic chemistry, so please find a quiet place and do your best to follow along and focus on this. We're going to start off with the very first reaction that we talked about in class, which is acid-base. Acid-base is a very simple reaction, but it is very important. And you might recall, if you were in class recently, that we talked about acid-base by itself, and then we moved on to talking about how the nucleophile-electrophile substitution reaction is really just like acid-base. So we're going to start off with those two things. I'm going to write nucleophile-electrophile. This is kind of a way to summarize electrophile substitution. We're going to put these two guys together. We're going to revisit those before moving into the new reaction mechanisms. All right, so in terms of acid-base, what we have is an acid, and I'll just write this. We'll start off with the base, actually. We have a base that has electrons that it can or wants to share. We have a hydrogen attached to a leaving group, often a halogen, but not always. And this hydrogen attached to a leaving group is what we call an acid. So the mechanism for this would be that the base shares its electrons with the hydrogen to make a new bond, and then the electrons holding between the hydrogen and the leaving group are going to be unshared. They're going to go to the leaving group, and that guy's going to leave. And that gives us what was the base is now attached to the hydrogen. It made a new bond. And we will have now the leaving group is all by itself with an extra pair of electrons. All right, there's often charges in there, but there you go. All right, I'll put some pluses in so we can tell that this is not kind of scooching into the nucleophile-electrophile section. All right, in the nucleophile-electrophile, we had a nucleophile, which is really the same thing as a base for the most part. It's something that has electrons it wants to share, but instead of having hydrogen attached to a leaving group, we had something else attached to the leaving group. Usually a carbon, but just something that we call an electrophile. And so the nucleophile shares its electrons with the electrophile, and the leaving group unshares electrons and leaves, and we are left with now the nucleophile is attached to what was the electrophile, and the leaving group is all by itself with a pair of electrons. So once again, the only difference between these two types of reactions is that in an acid you have a leaving group that's specifically attached to an H, and in a substitution reaction like this one, you have a leaving group that's usually attached to a carbon or something besides a hydrogen. But either way, it's the same general point of view from an electron of saying we have electrons that we want to share, and we share them and make a new bond. We have electrons that we want to share from a nucleophile. We make a new bond. And we have electrons that are being pulled by the leaving group, and we just let them go. The leaving group takes them and leaves. Same thing in the nucleophile-electrophile, the leaving group takes them and leaves. So the name acid-base is just something we created. The name nucleophile-electrophile is just something we created. But really, from the electron's point of view, they're being shared from something that has electrons to something that basically doesn't have enough, so that someone who wants to hog them can take them and go. And that's it. So let's look at some specific examples, and I'll ask you to try to figure these out. So let's start with acid-base. If we have ammonia, which is NH3, and a lone pair, and then we add that to, let's say, the hydronium ion, which is H3O+, these guys will undergo an acid-base reaction. So if you will, take a second and draw out the mechanism on your paper or on your screen with your finger, however you want to do it, and then figure out what the product would be of this reaction. All right, so let's locate first our leaving group. Our leaving group is most certainly going to be this O+ because it wants to unshare electrons. So this oxygen wants to unshare some electrons from a hydrogen so that it can have two lone pairs and two bonds that become neutral. That would leave this hydrogen kind of out of luck for electrons, so this hydrogen would need someone to share electrons with it. And that's where ammonia would come along. So ammonia could share electrons with that hydrogen, And that would result in us forming a new bond to the nitrogen. So that nitrogen would now have 4 bonds. And that would give a nitrogen a plus charge. And we would have, the oxygen would get a new lone pair, and it would still be attached to 2 hydrogens, and therefore it would make water. All right, so let's try another example under nucleophile-electrophile substitution. In this case, I'm going to give you a methoxide ion. Methoxide is kind of like methanol, only anytime you hear "ide" at the end of something, it indicates that it has a minus charge. So something like chloride or bromide, hydroxide, all of these have a minus charge. All right, and let's put that together with this guy right here, which would be 1-chloropropane. So, based on what we did above, see where the nucleophile is, where the leaving group is, and where the electrophile is, draw out the mechanism, and then draw out the product. All right, so I would say that the easiest place to start is to look for the leaving group. You can really start with a nucleophile. Obviously, this is the nucleophile. It's the thing that has too many electrons and wants to share them. This guy, the chlorine, is a leaving group, and so therefore the chlorine is pulling electrons off of the carbon that it's attached to. So the carbon that's attached to the chlorine is definitely the electrophile, and the way we know that is it's just simply the atom, usually the carbon, that's attached to the leaving group. So therefore, the oxygen that has too many electrons can share them with the electrophile that doesn't have enough and kick off the leaving group, and that would be our reaction. The result of this is that we would of course have a Cl minus, a chloride, all by itself off to the side, and then our nucleophile, which was the CH3O. The O is now attached to the carbon that was the electrophile, so we have a new bond in between this oxygen and that carbon, and then there would be 2 more carbons after that. So there would be a bond here, and then there are 2 more carbons after that. And that would account for our products. All right, so let's move into some new reactions, but keep in mind that these new reactions are still based off of these same reactions. The first new reaction I'd like to talk about is called addition. Addition, and there are 2 different types of addition that we're going to look at, but essentially addition reactions just involve nucleophiles and electrophiles getting together. There's 2 ways we can do this, but both of them end up looking like this. If you've got a double bond, then you essentially have 2 spots for stuff. You can add stuff to one side and you can add stuff to the other side without having to kick anything off. So we can break a pi bond and attach 2 new sigma bonds. So this is not meant to be carbon and deuterium or anything, but when we do an addition reaction, we can add something to one side of this double bond and something to the other side of the double bond. And we don't have to kick anything off. Instead, we're putting multiple things together, or we're adding on to a double bond. So we're adding on to a pi. So let's look at 2 different ways to do this. The first way we'll do it is driven by an electrophile. And really what it involves is an alkene. To consider for a moment what an alkene really is in 3-dimensional space, you may remember that an alkene has a sigma bond where 2 electrons are shared directly in between those 2 carbons, but then it also has a pi bond above and below. So the electrons in an alkene are being shared evenly between these 2 carbons, so there's not really a rush to move them anywhere, except that these electrons are loosely held and floating in space when they are in that pi bond. They're off to the side. They're not these nice sigma electrons stuck in between. They're way out there. And who's attracted to electrons? Of course, electrophiles are attracted to electrons. So let's draw the general scheme of this kind of reaction out. If we start with an alkene, and remember, an alkene has a pi bond, so electrophiles are attracted to it. The electrophile can basically take a share of those electrons. This would be an example of resharing, right? These electrons are not a lone pair, so instead one of the carbons has to take these electrons away from the other carbon and make a brand new bond to the electrophile. That would leave the carbon from which they were stolen left without enough bonds and not enough electrons. So this would look like something like this. We would have a brand new bond from what was the electrophile to one of the carbons. The other carbon wouldn't have enough. And in a second step, well, we have a carbon that doesn't have enough electrons. So now, this carbon that doesn't have enough electrons is the electrophile. A nucleophile can come in and fulfill its needs or its lack of electrons. And in a second step, we would get a brand new bond between what is our new electrophile and some nucleophile. All right. And so overall, what you'll see is that we've broken our pi bond of our alkene. We've attached an electrophile to one side, like this. We've attached a nucleophile to the other side. So I'm going to give you one example of this to try, and let's see how you can do. All right, we will start with CH3, CH, double bond CH2, and I'd like you to see what you can do if we add an H plus onto this. As a bonus help, I'm going to tell you that the pi bond is attracted to an electrophile, and indeed an H plus doesn't have enough electrons, so it's an electrophile. All right, so we would reshare electrons from that pi bond to the hydrogen. That would result in a new bond between one of those carbons and that new hydrogen. The new hydrogen, which I'll draw in white, has to go to the right side because it would give you the more stable carbocation in the center. If you did it the other way around, which we can imagine down here, this is wrong, by the way, but if you did it the other way around, we would have a new hydrogen on the center carbon, and notice that would give us a primary carbocation. It's a C plus with only one carbon neighbor, which is not as stable as a C plus with two carbon neighbors. So it turns out that this kind of reaction only goes in one way, but we'll get a lot more into addition reactions later. For now, what I really want you to be able to see is why electrons move the way that they would. All right, this can go in a lot of directions. We're not going to worry about the nucleophile being added on at this point, but really any nucleophile could come in and make a new bond. I know I just said we won't worry about it, but I'm a completionist, so if you have some Cl-, it's a nucleophile, and it can just add on there. We would end up with a brand new bond, so we will have added on one hydrogen, which I'll draw in white, to one side, and a chlorine, which I will also draw in white, on the other side. And that would give us a new molecule, starting with an alkene, breaking the pi bond, and adding one thing to each side. So the other type of addition reaction I will show you is nucleophilic addition. So again, I'm going to go backwards a little bit on you and say that the times that we've seen nucleophiles in the past involve a nucleophile being added to a carbon with a leaving group. And the deal is that that leaving group is pulling electrons away, like this, and therefore the nucleophile shares electrons with the electrophile, kicks off the leaving group, and gives us a brand new bond between the nucleophile and that electrophile, whatever it was. All right, so that being said, I'm going to leave that right there, and let's look at an addition reaction that starts with a nucleophile, just like the one I just drew, but adds it to a double bond. The double bond that we'll use here is a carbonyl, C double bond O. A C double bond O is a very polar bond between carbon and oxygen. It's not quite as polar as the bond between a carbon and, say, a halogen. However, the bond that we drew above, this one right here, is only 2 electrons being pulled away from this carbon. In the case of a carbonyl, you have 4 electrons being pulled away from the carbon, but by something not quite as strong. Still, the case remains that this is a polar bond, and so a nucleophile can share its electrons with a carbon that doesn't have enough electrons, which we call an electrophile, and kick off electrons to the thing pulling it away. this would give us a brand new bond between what was the nucleophile and that carbon. But instead of kicking off that oxygen completely, we don't have to break both bonds. We just break the pi bond. And that would give us an oxygen with a new pair of electrons, which is an O-. When we kicked off a leaving group, which was maybe a halogen, we would have a halogen with a minus charge. So it's very similar, except instead of breaking all of a single bond, we're breaking half of a double bond. All right, so at this point, we have an oxygen that's negatively charged, and therefore this guy is either a base or a nucleophile because it has too many electrons. And what can happen in the second step of this reaction is that you would usually add on an H+, because that's the easiest thing to do, or really it can be any electrophile. The mechanism for this would just be O-, shares electrons with hydrogen, and that would give us another new bond. This would be a new bond between what was the nucleophile, or was the base, which is the oxygen, and that hydrogen. And now everybody is stable. So let's consider both of these reactions together. In the case of electrophilic addition, we have electrons that are, or an alkene that's electrons rich, and so it's attached to or attracted to an electrophile. We add electrophile to one side, and then a nucleophile to the other side. In the case of a carbonyl, it's already electrophilic, so we can add a nucleophile onto one side, and then we add an electrophile to the other. In both cases, we're adding something to both sides, and therefore this is strictly an addition reaction. All right, let's practice this. I'm going to draw for you a carbonyl. I'm going to ask you what would happen if you were to add in H-. H- is something we haven't talked about before, but look at it, see if you can figure out how it's going to react, and go from there. All right, just like we said above, the carbon in a carbonyl is most certainly an electrophile because its electrons are being stolen away. And H- is a hydrogen with too many electrons, so it is, of course, a nucleophile. The nucleophile can share electrons with the electrophile, but we can't make 5 bonds to a carbon, so at the same time you need to kick electrons up to the O. That would give you a structure that looked like this. That's a single bond right there. We would have extra electrons on that oxygen, so that would be an O-. Most likely in a second step you would dump this into some water or into a little bit of acid. You could protonate or add an extra hydrogen to that O-, therefore turning it into an OH. Again, I don't expect you to be able to predict everything, but I do want you to see that really it's over and over and over again. Electrons move from something that has too much, like this nucleophile, or this nucleophile, or this alkene, or this nucleophile, to someone that doesn't have enough, like this electrophile, or this electrophile, or this electrophile, or this electrophile, or that H+, which is also an electrophile, or this electrophile. All right, let's move into our last type of reaction. Our last type of reaction is pretty much exactly the opposite of addition. It's called elimination. But elimination is just another acid-base reaction. Right? So once again, we're going back to acid-base. In acid-base, you've got a base with electrons. You've got an H attached to a leaving group. Share electrons from the base to the hydrogen. The leaving group gets to pull them off and leave. So that's acid-base. All right. In elimination reactions, we can consider that anytime you have an electrophile, that the CH next door is going to be acidic. And that can take 2 different cases. We could have a CH next to a carbon with a leaving group. Right? Again, this is the leaving group right here, and therefore that guy right there is the electrophile. Or we can have a carbonyl with a CH next door. A carbonyl's carbon is also an electrophile. So in both of these cases, the hydrogens on the carbon next door are acidic. we're going to especially consider today this case on the left. All right, so a carbon attached to a leaving group is in a pickle. It is, and I'll just draw a chlorine here. Chlorine's a good leaving group. This chlorine wants to leave and it wants to take electrons with it. Therefore, this carbon right here doesn't have enough. Well, there's two ways to make this guy happy. One is you could have a nucleophile come in, share electrons with that carbon, kick off the leaving group, and this would be just what we've talked about on the previous slide and the slide before. This would be a nucleophilic substitution reaction, where we would get a nucleophile attached and whatever bond was gone, or is still there, and then the Cl- would be gone. All right, that's one way to go. All right, let's cross that out and imagine another possibility. The other possibility is that instead of directly sharing electrons with the electrophile, we could have a base come in, so for example OH-, and that guy could take electrons away from the hydrogen next door, and then the electrons on the new pair of electrons on that neighboring carbon could share them in this direction. I know that this looks a little odd, but let's think about this. This carbon right here doesn't have enough. Either it can get some electrons from a nucleophile somewhere else in order to fulfill its needs, or it could ask its neighbor, hey, can you share some electrons with me? And the neighbor says, hey, I don't have any electrons to share with you. The first guy says, hey, what if you ditch that H? Then you'll have some extra electrons. And he's like, fine, let me find a base. And here's a base. The base takes the electrons off of the neighbor, therefore the neighbor has electrons to share with the electrophile, and everybody can be happy. So it's just another way of solving that problem that the electrophile has. The result of this would be that we get a new bond in between our two carbons, and it's going to make an alkene. The Cl- would come off, and the OH would remove that H and therefore become water. And so I have not added anything on, I've strictly removed things. So in an elimination reaction, you get rid of two sigma bonds and replace them with a new pi bond. So it's exactly the opposite of an addition reaction. This is once again an acid-base reaction, but it basically combines acid-base with your leaving group idea. So it's kind of putting together nucleophile, electrophile, and acid-base at the same time, giving us a new alkene. All right, so let me give you an example of this and see how you can do. We will start with this molecule right here, and let's say what happens if I add a strong base. I am going to give you this molecule right here. For reasons that we will talk about later, it is a base, but not a nucleophile. So, I'll give you a hint, you should draw in your hydrogens. But see if you can do an elimination reaction and see what product you get. All right, so like we just said up here, the CHs next to electrophiles are very acidic. So here's my electrophile right here. It's the carbon attached to the leaving group. All right, so that carbon's the electrophile, and therefore the neighboring carbons, which have hydrogens, can be quite acidic. And all of these are going to be exactly the same, so it doesn't really matter which one you pull off, but they're all going to be acidic. Our base can grab one of those hydrogens. The electrons holding on the hydrogen can be reshared to make a pi bond, and that would allow the leaving group to take electrons and leave and still have everybody happy. It would give you a brand new pi bond right here. Our big old tert butoxide would grab a hydrogen and become tert butanol. Our Br- would fall off as a bromide ion, and we have eliminated a hydrogen from one side and a bromine from the other side. Okay, those are our reactions for today. Let's summarize this really quickly, and then we will be done. To summarize, we are looking at electron-rich species sharing electrons with electron-poor species. An electron-rich thing could be a base, like OH minus. It could be a nucleophile, like OH minus. Or it could be an alkene, because an alkene has those pi bond electrons right here that can be shared. It's got extra electrons that it can share. An electron-poor species is something like an H+, or more often, an H attached to a leaving group, because the electrons are being pulled away, so that H doesn't have enough. It could also be a carbon attached to a leaving group, which we would usually call an electrophile, because the electrons are being pulled away. It could also be a carbon and a carbonyl, because the electrons are being pulled away, therefore making that guy an electrophile. So all of the reactions we talked about involved electrons being shared one way or another from our nucleophile, or our base, or whatever had extra electrons, to whatever didn't have enough. And that is my really quick summary of what we just did. Thank you very much. Please bring your questions to class, and we will talk about this soon. Thanks.